everyone. Thank you for joining us today for our ALS Webinar Wednesday series. My name is Kelly Hall. I'm a marketing coordinator for ALS North America, and I will be facilitating the webinar today. Before we begin the presentation, I do have a few helpful notes. If you are having technical issues with our webinar platform or any questions, type your message or question in the chat pod at the bottom right. You can also select the hand icon to notify me of your status and I can assist you. All questions regarding the webinar material will be answered at the end of the presentation. Our presenter today is Gary Blevins. Gary started his working career as a diesel mechanic for Mercedes-Benz trucks in South Africa. In 1988, he graduated with a certificate in mechanical engineering. He joined WearCheck Africa, a commercial oil analysis company, as a diagnostician responsible for evaluating the results of oil samples taken from machinery and then making recommendations for action based on these results. In 2001, he relocated to Saudi Arabia to manage a fluids analysis laboratory, primarily for Caterpillar equipment. Gary joined ALS in Perth, Western Australia in 2005. Now he lives in Cleveland, Ohio, and oversees the technical operations of ALS tribology laboratories in North America. Gary, thank you for taking your time to deliver this presentation today. I will go ahead and turn it over to you.
Hi, everybody, and thanks for joining us today. The title of my topic today is Coolant Analysis, and what I'll be doing is going through and going into a little bit of detail about coolants and the analysis that is performed on coolants. And the format I'll be following through with this presentation is, first of all, I'll be talking a little bit about the history and evolution of coolants, how they have changed. We will then discuss some of the formulations that are found in common or typical coolants. And from that, we will lead into the testing of these properties. And then lastly, we will look through some actual reports and just discuss what we can see with the analysis that has been performed on the coolants. All right, so starting up, first of all, I've got to figure out how to make this go down. Where is the button to move the slides forwards, Kelly? For some reason, I'm not seeing it.
You can use your arrow key.
Okay, thank you.
And it's located on the bottom
sorry,
right.
I tried enter. All right,
No
thank
worries.
you. I've located those. All right, so originally, engines were primarily air-cooled, and it soon became apparent to people building engines that they needed something a little bit more robust than just allowing air to cool the engine, and water started to become used as a coolant medium. The original coolants were principally water, and they may have a little bit of glycol added in winter to try and prevent freezing. But essentially, they were a true coolant in the sense that they were there to cool the system, but they did not have anything in them to try and inhibit corrosion of the system. So as it became apparent that just having water running in the engine would lead to corrosion, developments of coolants started to happen. Probably the first real coolant started to arrive in about 1950. And these would be water glycol mixtures that would contain some sort of inhibitor additive to try and stop corrosion from taking place. And the evolution started to move quite rapidly from then. And what we had been made were what we would now refer to as conventional coolants. But conventional coolants are coolants that contain an inhibitor additive that works by trying to prevent oxygen from coming into contact with the metal surface. So corrosion is a chemical reaction that occurs when you have got a metal, water, and oxygen available, and essentially the oxygen combines with the metal to form your corrosion, rust, if we're talking about iron. And these additives would try and break this chemical reaction from occurring principally by scavenging the oxygen. So as soon as the chemical reaction started to occur, this inhibitor would react with the available oxygen and prevent the corrosion from moving forward and basically stop it. So these additives, because of the way they work, are what we would refer to as a sacrificial additive. And what we mean by sacrificial is that they get consumed in service. So You put the coolant into service. Initially, all these additives are available to work, but as the coolant is being used in the system and reacting with oxygen, the additives start to become inactive. And so you would need to change these coolants quite frequently just to replenish the additive levels in there. Towards the 70s, early 80s, they started coming up with additives that could be added to the coolant in service to try and extend its life. These were normally a liquid that you would pour into the cooling system. Another popular method was to have like a spin-on canister that sort of looked like a filter, but inside that canister was the inhibitor additives. You would have this screwed on and plumbed into the coolant system, and coolant would flow through it and slowly draw additional additive out and into the cooling system to extend the life of the coolants. The problem, and also these coolants tended to be made on site. So in other words, a person would buy the concentrates and then mix them with water on site and put them into the cooling systems. The next sort of evolution of this came along is that what was found is that people were generally not very good at formulating these coolants. They would tend to think more is better, and so they would tend to overdose the coolant with additive. The other problem was that the water may not be of the right quality that we need for the cooling system. So they would generally be using drinking water, which contains dissolved salts, and that would then also affect the functioning of the cooling system. So from about the early 1990s, we started to see a switch towards pre-mixed coolants, where essentially you wouldn't buy the concentrate and then make the coolant on site. You would buy the coolant fully formulated in a pre-mixed form, and you would just pour it straight into your cooling system. And this solved the problem of the correct dosage rate. It also solved the problem of the wrong water being used. And that then sort of became the main conventional coolant that we would see in use. Finally got the slide to move. Around about the mid-90s, we started to see a completely new technology coming into the coolant space, and these were normally referred to as extended or long-life coolants. And these were coolants that were meant to be a fill-for-life type coolant, where instead of having a coolant that needed to be re-additized at intervals, could essentially be put in the system and left and work continuously in the system, typically for the life of the system. The principle that these coolants worked on is that instead of using a sacrificial additive or inhibitor, they used a barrier technology. Essentially, the additives in these coolants, and the additives were normally some form of organic acid, would coat on the metal and basically played out on the metal and prevent oxygen from being able to penetrate the layer and come into contact with the surface, and this would then stop corrosion from taking place. So there was a lot of interest in these coolants when they first arrived, because there's a lot of hassle in looking after cooling systems, and this certainly took away a lot of the hassle factor. However, these coolants didn't seem to work out as well as expected. We did find corrosion was still occurring in engines that were using these coolants, and in some cases you would even have accelerated corrosion, more serious than what we had seen on the conventional coolants. This was eventually attributed to a number of factors, but one of the main factors is that this barrier that forms from the organic acids can be disrupted, particularly if there's vibration or aeration occurring in the system. So that led to what we now call hybrid coolants. And a hybrid coolant is simply a mixture of an organic acid formulation with something of a traditional inhibitor formulation, sacrificial inhibitor formulation, and you're basically trying to attain the best of both worlds. So the barrier works 90% of the time, but the 10% of the time that it gets disrupted, the conventional process will still prevent corrosion from taking place. Excuse me. All right, moving into a little bit more detail on the coolant formulations. Coolant generally starts with water. Water is still one of the most popular means of providing coolant, because water is very good at transferring heat. Its ability to absorb heat energy and to move it through a system and dissipate it through a cooler is very effective compared to a lot of other fluids. And this is why it is still a very popular coolant type that we see being used in engines and even into increasingly with EV vehicles. The batteries and the charging systems also need to be cooled, and we're seeing the same sort of thing happening where they're using water-based coolants to provide this cooling on those vehicles. So we start with water. Excuse me a minute to keep the throat working. So we start with water, and then we will mix it with glycol. It's historically ethylene glycol was the main glycol used. Increasingly, we're seeing propylene glycol being used now. Essentially, both of these are to try and provide freeze protection for cold environments in winter, and also some assistance in boil protection to try and raise the boiling point of the fluid. The general ratio of water to glycol is generally 50-50. Nearly all coolants will be prepared at that dosage rate. We will then add our inhibitor package. So if it's a conventional coolant, we'll be using our sacrificial additives. If it is a organic acid, it will be using the organic acid inhibitors, or it'll be using a combination of both. And increasingly, we're seeing these hybrid coolants becoming the dominant coolant type that we see being used now. And then lastly, we put a dye into the coolant, and this is just purely to give it an identifiable color. There is a range of different colors that coolants can be dyed, but the dye itself doesn't provide any benefit to the coolant. It's just merely a means of being able to give it a specific color so that we can identify it. Just through convention, there's no real rules about this, but just what we tend to see happening is that conventional coolants are generally either dyed green, and that's probably the most popular color for a conventional style coolant. They can also be purple, blue, pink. Those are typically the colors that we're seeing conventional coolants being dyed. The hybrid or long life coolants are typically red is a very popular color. Orange is a popular color. Yellow and blue are also popular, more in the European market than in North America. Something else that can be done with the dye is that there are some coolants where you get a color change that can be triggered by the dosage rate. So you can get a sense of whether or not your additives and your water is in the correct ratio based on the color. There's a color change if there's too much water or not enough water in the coolant. Some of the coolants will also contain a phosphorescent dye that makes it easier to identify coolant leaks. So if you've got coolant leaking out of a system, the coolant may boil away, but it'll leave some of the dye behind. And these can be spotted using dark light, that type of thing. Conventional coolants have a wide range of additives that they can be present in them, and normally there'll be more than one. Sodium nitrites is probably the most common inhibitor we're seeing in use in conventional coolants. These are very effective at preventing corrosion on iron. So, excuse me again, sorry about this. But sodium nitrites doesn't work very well with aluminium systems. So if you have got aluminium, you tend to find silicates is more common in the conventional coolant space. So sodium nitrate, as I said, is the most common, and monitoring a nitrate depletion in a coolant is a very essential part of monitoring the life of these coolants and making sure that they still work effectively. On screen, we've got a little dip strip type methodology that can be used. This is very useful for a workshop or field environment for checking the coolant state. In the lab, we will use redox reactions or other methodologies for measuring exactly how much nitrite is still there and how much has been converted to nitrate. Essentially, what's going on for people unfamiliar with this is that you will dose the coolant with sodium nitrites. When nitrite reacts with oxygen and becomes nitrate, just basically means it's got an extra oxygen added to the molecule, and monitoring the conversion. Once it becomes nitrate, it's no longer effective in the system. So by monitoring both compounds, we can see the conversion rate from one to the other. If you have a engine that is primarily aluminium rather than cast iron, then the sodium nitrate doesn't work very well, and so these tend to use a silicate inhibitor. And so you tend to find that these tend to have fairly high levels of silicone in the silicates in the coolant to prevent corrosion. There are problems with using silicate-based coolants. I'll get into those in a little bit more detail in the next few slides. Your extended life or long life coolants, these will often advertise the fact, or easily identified by the fact that they will advertise that they do not contain silicates, they do not contain phosphates or borates. The reason they're advertising this is that the presence of these additives can form solids in the coolant. And this is the problem that I was referring to earlier when I was saying that people were overdosing the coolant. If you have too much additive present, it will tend to crystallize and it will form hard deposits. These can be abrasive and they can also block the system. And so the formation of these compounds is not desirable in a cooling system. Anybody working with cooling systems for any length of time would have come across a cooling system that's full of a green gungish type sort of material, and that's the silicates forming or crystallizing within the system. So, as I said earlier, the main reason people tend to promote the use of these coolants is the fact that it can be a hassle-free coolant. You put it in, you don't need to worry about it again. What is actually in the coolant to provide your corrosion protection is some type of organic acid. There's a bunch of them listed on screen here. Generally, the first three are the ones that are most commonly found in these type of coolants. They provide protection against corrosion for iron, copper, and aluminium, which are your main metals that you'll find in your cooling system. There is several more that can be used, and different coolant manufacturers will use these compounds in different dosage rates and different mixtures depending on what they believe works best for a cooling system. So there is some variation from one coolant to another, but essentially it is an organic acid that has been put in there that is forming a barrier on the metal to try and prevent the corrosion from taking place. Can we mix a coolant? And the simple answer to this is no. We really shouldn't mix two different coolants together unless we properly understand what it is that we're dealing with and what the chemistries are that we are working with. So as a general rule, strongly recommend to people that we do not mix coolant unless it is an emergency situation. We have no choice but to keep a system running, you have to put in a different coolant. When that occurs, recommend that at the earliest opportunity, we need to drain what is in the cooling system and refill with whatever is the main coolant that you would typically use in the system, just to get that mixture out of there. The problem is that because different coolant manufacturers use quite different chemistries in their coolant, when we start mixing these together, we can get reactions between these additives, and these reactions can be unpredictable unless we properly understand the formulation of each of the coolants. So the general advice is not to mix coolants if at all possible. The hybrid coolants are literally a mixture of organic acids and one or more of the sacrificial type inhibitor additives. And the most common one you will find in there is sodium nitrite. This is particularly common if the coolant is intended to be used on an engine that's got cast iron cylinder heads, cast iron blocks. There are other inhibitors that will be used if we're dealing principally with aluminium components. Sodium nitrate is not very good at protecting aluminium, particularly at higher concentrations. It can become problematic to the system. which kind of suggests that we need to be careful as to what coolant we're using into what system to make sure that they are compatible with each other. Just something that is to bear in mind is that one of the common threads that we see occurring with engine technology in particular is the drive to make more power from less. Basically, engines are tending to get smaller, and power is tending to get larger, and this ultimately means that to generate more power, we need more heat. So we've got systems that are getting hotter, producing or capable of producing a lot more heat to produce the power output that we want. And that means that the cooling systems are having to deal with higher heat loads, particularly under peak load conditions, than what they may have been dealing with historically. Sorry, I have to keep taking a sip of water to try and keep the throat working. A number of research bodies have looked into what causes failures on engines, and most of these conclude that at least half of engine failures can be attributed back to the coolant. And in my personal experience, I've seen it probably rated even higher than that. Often we'll have an engine that has failed, possibly it's failed a bearing, for example, but when we strip the engine down and examine it, we'll tend to find that there was in fact a corrosive problem in the cooling system that should have allowed coolant to leak into the engine oil, which had ultimately caused the bearing failure. So the origin of the failure was through a poorly maintained cooling system. Moving on to the testing that we do, there's a range of physical tests that we can do to the coolant to understand the physical condition of the coolant. No particular order of importance, but we've got on the list here starting with the pH. And again, I'll go through a detail of each one of these tests on the future slides. But essentially, we measure the pH value. We can measure things called reserve alkalinity. We can measure the glycol content, chloride content, nitrite content, conductivity, and quantify the organic acids that are present in the coolant. We can also look for contaminants in the cooling system to see anything that might be getting in there that shouldn't be in there. And then importantly is to monitor corrosion. If we can monitor the metals that are present in the system, if we see those metals starting to be dissolved into the coolant, that is a strong indicator that corrosion is occurring within the system. All right, pH. Water that we start with has a pH of 7. We will put additives into this coolant. Generally, those additives tend to be more alkaline. And so what we see is that the overall pH value of a coolant tends to rise above 7 to somewhere around about 8. So most new coolants, when we test the pH, will test somewhere around about 8 on the pH scale. And it should be stable. The most important thing to be aware of your pH value is that you want it to run somewhere between 7 to 8, possibly as high as 8.5, but you really don't want it to go much higher than that, and you certainly don't want it to go much lower than that. It should also remain very stable. So if you keep checking the pH over an extended time frame, whatever its original value was, that's what you want it to stay at. If you see changes in pH, it's indicative of something happening to the system. That could be contamination or degradation of the coolant taking place, or a combination of those things. But as soon as we see shifts in the pH value, that starts as a very early warning indicator that this coolant is not working very well in this environment, and something is going wrong with this particular coolant. So for our conventional coolants, the older style coolants, somewhere between 8 to 10 would be a typical range. You very seldom see them as high as 10 nowadays. All the newer formulations tend to run between 8 to 9 maximum. And unusual to see a coolant go up to 10 now. For your longer life or your hybrid coolants, generally they're running between the range of 7 to 8.5. And more typically around the value of about 8 would be a sort of a typical value of what you see the coolant pH. And as I say, Ideally, whatever its starting value is, it should remain at that value. We don't want to see changes in the coolant over time. Very common measure done on cooling systems is to quantify the sodium nitrates, because this is your principal inhibitor additive that's used in most coolants. Any heavy-duty coolant will invariably have sodium nitrate as part of its chemistry. It's just very effective at preventing corrosion of cast iron or steel components in the cooling system. As this additive gets consumed, we will see a drop-off in the nitrate value, and if you're monitoring the nitrates, you'll see an increase in the nitrate quantification. So it's just really good to see how the inhibitor is being used. If you see a rapid depletion, it means that there is something that's trying to drive a lot of corrosion in your cooling system, and this means two things: that you may have a problem with the cooling system and maybe running too hot or overstressed. It could also mean that whatever else you have in that coolant that should be inhibiting corrosion is not working. So if this is a hybrid style coolant, it means that the organic acids are not doing their job. This could be through cavitation. This could be through excessive vibration. It could be through electrical current. There's a range of things that can cause this to happen, but it's an early warning indicator that this coolant is not surviving very well in that environment. All right, we measure the organic acids principally by using ion chromatography or ultra-high pressure liquid chromatography. Basically, these are complex instruments. They are laboratory-grade equipment. It's not something that's easily used in the field environment, but it can quantify, and particularly important for coolant monitoring, it can quantify the organic acids for us. And this enables us to see things like, is there a mixture of coolants being put into use? Are these additives being removed from the coolant? This would indicate that there's some sort of stress going on in the coolant. So it gives us a snapshot into that aspect of the physical property of the coolants. We do an elemental analysis mainly for the metals. We can also look at some of the additive chemistry directly. So these the main elements that we're monitoring are things like aluminium, iron, copper, and lead. These are the metals that are most commonly found in cooling systems. And if we see an increase in any of these elements, it is an indication that corrosion is taking place in the system. So even if all the other properties look good on the coolant, if these are increasing, we have corrosion. There is something causing corrosion within our cooling system. Reserve alkalinity is a measure of the coolant's ability to absorb acid. The coolants don't normally get exposed to much as acids in from the environment, that type of thing. But there is one potential problem with the coolant, and is that your glycol, when it degrades, glycol can thermally decompose, and it will start doing this as low as sort of 80 degrees Celsius. When this degradation happens, or thermal degradation occurs with glycol, it does tend to produce acid components. So some coolants, we know that we're going to see thermal degradation of the glycol. We know that acid is going to be formed, so we need to buffer the coolant to absorb that acid to prevent it causing any sort of acid corrosion in the system. The reserve alkalinity is a means of measuring that buffering potential. And how much buffering the coolant can take depends very much on the chemistry that the formulators put into it. So we do see a range of potential values that could be reported. Conventional coolants generally have higher RA than the newer hybrid or long life coolants, but essentially what you see on screen, 8 mils to 20 mils would be typical for an older style conventional coolant. 2.5 to 5 mil will be what you would see for the newer style coolants. In of themselves, it's just telling us what the coolant's ability is to absorb acid. It doesn't necessarily tell us the coolant's ability to stop corrosion. So you may still have very acceptable reserve alkalinity of a coolant, but if the inhibitor additive, say sodium nitrate, has been consumed, corrosion will still happen. The RA itself will not inhibit corrosion in the system. Conductivity is something that's fairly quick and easy to measure on the coolant. And the reason we measure it is that the chemistry in the coolant is going to provide a certain level of conductivity in the coolant. Generally, pure demineralized water is very poor conductance. The electricity just simply won't flow through it easily. As we start adding things to the water, the conductance increases. So the first thing we need to establish is, all right, we've got a new coolant. What is the typical conductivity of this coolant? Then we look for changes. And if we see changes, and generally the changes that it increases, we see increasing conductivity in the coolant, that could be through contamination of the system. And a very common cause of this is contaminated water being added to the system. So if somebody's just drawing tap water and adding it to the system, that will definitely drive up the conductivity. So that is a very quick way of identifying that particular problem occurring in the coolant. It can also change as chemistry changes. And so, again, it's another easy way to tell that some sort of chemistry in the coolant is changing, and this could be a precursor to bigger problems in the cooling system. Total dissolved solids is a measure of how much solid content is being carried around by the coolant. The principal way to do this is to filter out the solid particles and then weigh how much solid material is filtered from the coolant. You can also do it by using what they call a TDS meter. A TDS meter is a version of a conductivity meter that measures conductivity and then converts it to a total dissolved solid content number. Be aware that this number doesn't correlate very well to an actual filtration methodology, and that's just inherent within the formulation of the coolant. It does tend to interfere with the measurement, but at least if you trend it, you can get a sense of if this is going up or down. Obviously, having solids in your coolant is not desirable. It'll wear moving components like your water pump, and also it can start to block narrow tubes and pathways, etc. Measure of hardness. This is basically just measuring your calcium carbonates or your other carbonates in the water. And these are found if people are using, say, tap water or drinking water. You will tend to have these present. They are important for human health. You don't want to drink water that does not have these, but they are not beneficial to a cooling system and can lead to deposits. And that's our main concern with having calcium carbonate or any of the other carbonates in there, is that it will deposit in the system. I have a slide a little bit further on that will show more detail on that. But there you've got a typical picture of what kind of deposits out from these when they are present in the water. So they occur naturally in water. So if you take water out of a river stream, you will find it's quite high in these deposits. And this is a purely natural process. But unfortunately, when they are in the cooling system, they will tend to be deposited out, and they will tend to form there's two problems. First of all, it's reducing the flow because it's taking up space. And then the second problem is it's also very good at insulating and doesn't allow easy heat transfer through the surface. So it inhibits the ability for heat to be managed in that system. So different engines and engine manufacturers have different levels as what they believe is acceptable for this. So we've got a couple on screen there. Basically, some engines are more sensitive to it than others. So it depends on the design of the cooling system, design of the radiator system as to how much it can tolerate. But as a general rule, you want to try and reduce your hardness as much as possible and try and have as little dissolved solids content in your coolant as possible, which means we have to use high purity water when we're making up or topping up a coolant system. So water is very good at dissolving this material, as I was saying, and if we are just using even rain runoff water may contain some of this. So we just need to be careful as to where we're sourcing water from to go into coolant systems. All right, antifreeze or glycol is added. In principle, and originally glycol was added to cooling systems to prevent freezing. And anybody living in particularly the northern hemisphere will be familiar with how cold winters can get and the fact that water will freeze at typical overnight winter temperatures. So we needed a means to prevent this water from freezing, and glycol was just a very simple, easy methodology to do this. There are two main glycols in use. Ethylene glycol has been used for a long time. Propylene glycol is becoming more popular now. The main reason for the switch is propylene glycol is less hazardous than ethylene glycol. So it's all about the toxicity is what the concern is. They both work in a very similar way within the system. Glycol can degrade, and this is a natural process, and is one of the things that will limit the life of a coolant, is that your glycol will tend to thermally degrade over time within the system. The hotter the system, the more quickly it will degrade. So if we see glycol falling away rapidly, that would tend to suggest that the coolant has been subjected to higher temperatures than what is ideal. Essentially, when it is breaking down, one of the degradation products is an ammonia. And if you smell ammonia coming off your cooling system, it's a very strong indicator that this degradation is happening. Other things that we will see from an analysis side is we will notice that the glycol content is dropping away. One of the products is water, so you don't necessarily get an overall loss to the cooling system. The glycol is converting itself to water in the system. So it seems kind of magical sometimes that you just slowly see glycol disappearing, but you don't seem to lose anything out of the cooling system. The other thing we will see is that the pH value will drop because the compounds that are being formed as the glycol degrades are acidic. And this slide is a little bit about the difference between ethylene and propylene, and the fact that propylene is considered less harmful as a toxin, and this is why there's this drive to start using it. However, I would caution that coolants, particularly because of the inhibitors and everything else that's in them, should generally be considered as a hazardous or toxic material. I certainly wouldn't recommend just draining it into a waterway or something. It should always be treated as potentially harmful material and kept containerized and marked clearly, and not allow pets and things to drink it. Measuring glycol is most commonly done by measuring the refractive index of the coolant. As we add glycol to water, it changes its refractive index. And by measuring the refractive index, you can then calculate how much glycol is present in the fluid. As I say, it's the most common way that it's done. You can get little handheld devices like shown on screen, and these can easily be used in a workshop environment for checking coolant to make sure that the concentration is correct. Why we don't just use pure glycol instead of water is because glycol is not as effective as removing heat from the system as water is. So a mixture of glycol and water, it's not as good as water, but it's not as bad as glycol, and so we get to a compromise position that we can run with. And that's essentially what this slide is trying to explain to us, is just showing that water has a value, or a calorific value of 1. Water is a base unit for the SI unit system. And then glycol is 0.58 or nearly 0.6, we can say in round numbers. So it's only about 60% as efficient at moving heat around the system as water is. When we mix it with water and glycol together at 50-50, we end up with something that's about 0.9. So we only lose about 10% of our heat carrying capacity, but we gain the benefit of it not freezing. And this is why this is the most sort of common ratio that we will find your water glycol contents in. A little bit more detail on the freeze point. Essentially, what glycol does is it prohibits the formation of ice crystals in water. So it stops the water from crystallizing and forming ice. And the more glycol you have, the more this effect takes hold. And so what you can see on the left-hand side of this chart is that we get the steady decrease in the freezing point as we add more and more glycol. But once we get much above 60%, we see an inversion. And basically what's happening is the whole chemistry has changed. We've now got water and glycol rather than glycol and water. And that changes the behavior of this compound. And we actually see an increase in the freeze point again. So once we reach about 60%, there is no real value in adding more glycol to the cooling system to try and lower the freeze point. You're not getting that much benefit anymore, and you start reaching a point where you can actually start going the wrong way. At 50-50, we generally are down to minus 35 Fahrenheit as our freeze point. That should work for most applications. If you need to go below that, I would suggest speaking to whoever you source your coolants from and start discussing what can be formulated to work at lower temperatures. And it's something that shouldn't be taken on just lightly. You would need to do research to establish what will actually work at the kind of temperatures that you're going down to if you are going down to much below, say, minus 50. How to take a coolant. One of the things to be careful of with coolant is A, it's hot, and B, it's under pressure. So the main method for taking a sample of coolant should be through a dedicated sampling point or valve on the system that allows you to bleed off some of the coolant in a controlled manner from the system. There are a number of different types of valves on the market or installed on equipment for this purpose. Some of them use a screw-on fitting. Some of them will use a push-on fitting. The methodology for actually taking the sample will depend on the type of sampling valve that's installed, but essentially, please follow the instructions on how to do this. It is a potentially risky activity just simply because of the heat that this coolant can be at when we are taking the sample. If the system does not have a sampling valve, and if you are sampling a cooling system on a regular basis, I would suggest installing a valve to take samples. But if you do not have a valve, then to take a sample, we're going to need to depressurize the system. And the system is pressurized thermally. The heat is what causes the system to build up pressure. So to depressurize the system, we need it to cool down. So you're going to have to shut the system down, allow it to cool. And once it's come down to close to ambient temperature, we can then start to open up the system to take a sample. We need to be careful in this process, as there would often be some residual pressure in the system even after it's cooled down. And we need to make sure that we have allowed sufficient time for the system to cool down before opening up the system. We do not want to suddenly release the pressure because that could trigger boiling of the coolant when we do that. And that potentially could even damage the equipment itself. The other problem with sampling this way is we need to ensure that we're getting coolant out of the main coolant circuit. So it means being able to get into the main radiator or header tank or something like that to draw coolant. We don't want to draw coolant from the overflow tank, which may not be used that much. So the coolant in your overflow tank might look good, but in the main system may have a problem. We need to try and access the coolant from the main system. And again, this is another reason why I would suggest using a valve is a lot more effective than trying to just open up a system and draw a sample. If we are drawing a sample without a valve and we're using one of these handheld little vacuum pumps to draw the sample into the bottle, these are often used for taking oil samples. Please be careful not to use one that's been used for oil samples for taking a coolant sample, as there is a risk that oil that is inside that vacuum pump may get into the coolant sample and will show up in the analysis as potential oil contamination of the coolant. All right, what tends to go wrong with cooling systems? Basically having the incorrect glycol content, inhibitor concentrations, using the wrong water. and then general problems with the coolant system itself, where the coolant system may not be working effectively because of a particular problem with the cooling system. If we don't maintain our cooling system, there's a whole range of problems that can occur from this. And the main issue is that we increase the risk of a catastrophic failure of this piece of equipment. Incorrect coolant temperatures tend to lead to seizure of components and physical damage of components, which can lead to complete failure of the piece of equipment. So we really want to make sure that our coolant systems are managed effectively and are in a healthy condition. All right, things that cause coolant to degrade. A very common problem is that the coolant becomes contaminated, and the most common contaminant is just plain tap water. People topping off a cooling system with water drawn from a drinking tap, it introduces your chlorides and that type of thing into the system, which then begin to play it out. It will also dilute down the additives that are in the coolant as well. As the more water we add, you lead to a coolant that is no longer additized sufficiently for the application. Cavitation and pitting of liners is a particular problem that we see on some engines, but basically what we've got is air bubbles forming against the side of the liner, and there's one of two mechanisms that produce these. Some of it is because of air being pulled in and moved around the system just from the way the coolant circulates, and basically what you have is a water-air mix being shot against the liner, and you've got these air bubbles hitting the liner. Another more common problem, though, is vibration. The firing of the cylinder generates a shock wave through the liner, and that shock wave then can generate bubbles off the surface of the liner and bubble them away. And this is fairly common on some engines as a particular problem. Now, when this cavitation occurs, this bubble tends to break away barrier protection. So your organic acid style coolants are particularly susceptible to this issue, and you will tend to find a lot of pitting at the top end of the liner occurring because of this. And once we form a pit, you tend to have an area where the chemistry to form corrosion, it becomes ideal. And so we tend to form more corrosion inside the pit, and the pit steadily get bigger and deeper and actually can start to channel into the surface. So here we have an example. You can see that this pitting is occurring in a vertical line, and that would tend to suggest it's flow related. The most likely that is the leading edge of the flow reaching the cylinder. But the fact that it's also towards the top of the cylinder also suggests that vibration is playing a role and forming these pits. Now, as I said, one of the problems that tends to occur is that you get these ideal corrosion conditions in one of those bigger pits, and it starts to tunnel. It will literally drill right through the liner until you get water transferring into the inside of the cylinder from this process. There's three types of corrosion that tends to be generated inside a system. We've got electrolytic, we've got galvanic, and we've got crevice corrosion. What type of corrosion is occurring just depends on what's going wrong with the cooling system or with the system as a whole. Your electrolytic is generally driven by stray current. We have electrical systems that are attached and bolted onto our engines. If that electrical system is not earthing correctly or has some sort of electrical leak, that will then allow electrolysis to be driven inside our cooling system. And depending on the nature, can be potentially serious. Your electrical connections and grounding is important to try and prevent this type of corrosion from occurring. So one of the side effects of having stray current in the coolant is that it will degrade the glycol, and this is where your ammonia becomes pretty noticeable. So again, if you get a strong ammonia smell coming from the coolant, particularly if you open up the system to check levels and top it up, etc., and you notice an ammonia smell, this is one of the common causes. It's either the coolant is being heat stressed, or you have got stray current being driven through the coolant that's causing this process. And from the testing, we will tend to notice a drop or a rapid drop in the glycol content in the coolant. Your galvanic corrosion, generally this is a design problem. If the system is designed properly, this shouldn't be an issue, but it's essentially where you have got dissimilar metals that have been bolted together. You can get electrical potential driven between them, and this can kind of drive a corrosive action through the flow of electricity from just simply bolting these two bits of metal together. To be honest, in most installations, this is not a big problem. But where you've got sort of custom-built equipment, this could be a problem. And in the marine world, this is particularly problematic because there might be salt water in part of the systems, and salt water is particularly good at driving this kind of corrosion. Crevice corrosion is very similar to what I was talking about with pitting, is basically where you get a corrosion starting at a point and it just keeps driving through. Of course, we tend to notice this more where we've got a water trapped in an area that it shouldn't be trapped, and that's the examples they're showing on screen with bolts and threads that have been eaten away from this, just to sort of illustrate what can happen. But it can potentially happen in a cooling system if we've got a blocked area where we've got a small content of water or fluid trapped, and then this crevice corrosion type action can start up and eat through something. And it can eat through pretty quickly, so it doesn't take very long for this to punch a hole in something. All right, some examples of what tends to go wrong with the coolant. Now, what we're showing on screen here is a formation of copper sulfate. And to do this is we've got copper in our radiator cooler core. And if sulfur or sulfur compounds have got into the cooling system, they can react to form this greenish, bluish powder. It turns white as it dries out. Obviously, forming this is not good in our system. It will damage the tubes, so the copper becomes weaker as a process of this reaction. And then also this material can become abrasive and also inhibiting water flow by just blocking up tubes and that type of thing in the system. We also, and this is a more common problem, is that what we're looking at here is salts that have been plated out. So these salts could be coming from dirty water, or they could be coming from a mixture of coolants that have been put together where you've got particular silicate can react and plate out and form these kind of deposits that are forming in the cooling system. The main way to try and stop this from happening is to make sure that you've got the right formulation of your coolant and that you don't put tap water, or you only use demineralized water in the cooling system if you top the system up. Again, this is an example of what tends to happen in the pipework when you have got, to get the level that we're seeing in this picture, we would need something like almost river water being used in the system as opposed to tap water. But it's where you've got a high degree of dissolved salts in the water, it will plate this material out inside the cooling system. Boiling point is increased by pressure, and we don't increase the pressure very much in a system, but the more pressure that we have in the system, the hotter we can make the coolant without it boiling. And obviously we don't want the coolant to boil in the system because it becomes very ineffective at moving heat once it starts boiling. So most cooling systems are under pressure to try and raise the boiling point to some degree. All right, now it's time to go through a few reports and just show numbers on the screen and kind of what they're telling us. What we're looking at here is the first one is a conventional coolant. We can tell it's primarily a conventional coolant from the formulation. But what we're looking at, this sort of coolant, typically, this is more of a hybrid style coolant, and it should have the sodium nitrate running at about 800 to 1200 ppm. And so at sort of the 250 here, we're well below that. there is no, we can see some black material is being deposited out. This could indicate that some sort of black oxides are present and some sort of corrosion is starting in the system. However, we're not really seeing much iron. So corrosion itself is probably relatively light at this stage. But what we're looking at is a situation that if we keep running this coolant like this, we are likely to see an increase in corrosion over time. So this would be a good opportunity to, in this situation, really we need to replenish this. So it would just be a drain and refill will probably solve this particular problem. All right, here we've got a sample where we can see our nitrates are pretty strong. So it's a conventional style coolant. But what we keep seeing in this system is the presence of oil on the surface of the coolant. So this would suggest that oil is getting into the coolant somehow. And if oil is getting into the coolant, it's normally coming through from the oil cooler. It's the area where these two come and interact with each other. And if you've got a leakage in the oil cooler, there is a risk that the oil pressure is higher than the coolant pressure, so the oil tends to get forced into the coolant. However, when the system is shut down and the oil pressure drops to zero, you can start to push coolant the other way. So you may start to find coolant in the engine oil as well in these situations. When they describe this as just a sheen, it means it's a very thin layer on the surface of the coolant. It means it's probably not that much oil, but it's an indication that a leak has started. Of course, the other thing we've got to look at is, did this happen when they took the sample? As I was referring to earlier, if they have used one of those sample vacuum pumps that was previously used for an oil sample, this could be contamination of the sample and not necessarily a problem with the coolant system itself. Here we have a coolant that has become very hazy. Now, coolants become hazy when we have got an overconcentration of additive and the additive is beginning to crystallize. And if we look at our sodium nitrate results, we've had extremely high levels here, running at nearly 4,000. And this is more than likely what has caused the problem, is that this coolant has been overdosed. This has allowed the additives to begin to crystallize and form solids in the cooling system. And so it leads to this particular situation. When you see this, my recommendation is we need to drain and try and flush the system. So we want to drain the coolant, fill it up with water, clean water, run it for a few minutes to try and pick up any dissolved salts we can, try and resolubilize it back into the water, then drain that water, and then refill with proper coolant again to see if we can clear this material out. And here we have an example where we're seeing corrosion starting to happen. So we can see that iron has now risen to 12 ppm in the sample, and this would suggest that we're starting to see the start of active corrosion in the system. What's also concerning is we're seeing a moderate deposit of brown particles. Now, these are almost certainly to be iron flakes, basically rust that's been carried around in the coolant. The most likely scenario is that our inhibitor level is too low. This looks like a conventional coolant. It's not a hybrid coolant. It's just a straight conventional coolant. And we need higher levels of additives to try and stop corrosion in the system. So again, what we should be doing here is, because we're seeing active corrosion, we need to flush this material out and then refill with a new coolant, and then just monitor it closely to see, is the corrosion dropping off or is it accelerating? If it's accelerating, we might want to dig further and see, do we have high temperatures or something that is driving the corrosion we're seeing in this particular sample. All right, here we've got more serious corrosion going on. So we're seeing much higher levels of iron. We're noticing that the sample is now being described as very hazy, almost opaque. There's also a lot of brown deposits, and the coolant itself has turned brown from this. There generally isn't a brown coolant on the market, so this would suggest that this coolant is just carrying lots of rust around, which is discolored it. Again, our nitrates level are very low. Again, it looks like a conventional coolant. So in this situation, we really do need to flush this thoroughly now to try and get the as much of this corrosive material out there. We probably want to fill it with a new coolant, run it for a short period, and probably drain it again and refill to try and see if we can get this one to come back to normal again. All right, here we have a coolant that is driving a lot of copper corrosion. So iron isn't corroding, but copper is. Now, I can also see that our additive levels suggest that this is a conventional coolant, and it is extremely heavily dosed with sodium nitrates. And a lot of this is converted. So it suggests this coolant has been in use for a long time. And what I suspect has happened here is that the additive that is inhibiting copper corrosion has stopped working quite some time ago. And this is leading to the rapid increase in the copper corrosion that we see going on here. Again, the recommended action at this stage would be to flush the system completely and refill the coolant, and also make sure that what formulating coolant are we actually using here. This additive level just doesn't look typical for a coolant system, so we've probably got either mixtures going on here or something that has been heavily overdosed but not correct for the application that this coolant is being used in. Here we've got an interesting one. What we're looking at is extremely high levels of aluminium in the cooling system. The coolant has been described as hazy, so it doesn't look clear. It's got a lot of the typical additives that we would see in coolant, so it looks like a normal coolant, but the pH is very high. And something we wouldn't normally do on coolant, but because of what was suspected to be done here, they've tested this coolant for urea and found that there is urea content present. So what has most likely happened here is this cooling system has been dosed with DEF, and that is strongly alkaline, and alkaline solutions will dissolve aluminium. So what we're seeing here is somebody has accidentally put DEF into a cooling system, and this has triggered a very strong corrosive attack on the aluminium components of the system. Literally, when pH is much above 10.5, once it reaches 11 and greater, your coolant is literally dissolving the aluminium, and this will happen extremely rapidly. This is an urgent situation. This coolant needs to be drained as soon as possible from the system. The system will need to be flushed and checked to see how much damage has actually occurred, and then putting the correct coolant back into service. Have another sample here of a very poor looking coolant. We've got extremely high iron level. We've got extremely high copper level. So a lot of corrosion going on in the system. We can see visible rust in the sample. And when we look at our additive levels, they are very, very low. So what we're looking at here is what looks like almost straight water in the system. Whatever coolant was originally in the system is long gone, has probably been constantly topped up with water until it's completely replaced the original coolant, and this has allowed a lot of corrosion to start taking place. So again, the reaction we need here is very much depending on the current health of the system. Generally, a system in this condition is not going to be in good health. We need to establish the health of the system. We would need to remove this coolant as quickly as possible and replace it with something that is better suited to working in a cooling system. But normally when I see results like this, you're probably looking at a system that's due for a rebuild because it has been pushed too far. Okay, everybody, that concludes my presentation for this webinar, and now open to address any questions that have come up.
Yes, thank you, Gary. We will go ahead and open it up for questions now. We did have some questions that came in, but for everyone else, please feel free to write out your questions in the chat section at the bottom right. We can give everyone a few moments, and I'll go ahead and start the questions that came in. The first question was from Lawrence. He asked, Mercedes-Benz used to require special coolants. Are these really any different than other commercial coolants? And are all coolants created equal today?
Sorry, Kelly, I lost audio on you toward the end of that question, but I can see it on screen. All right. First of all, Mercedes-Benz are not alone in this situation. A lot of engine manufacturers will push use of a particular type of coolant in their systems. And my recommendation would be to try and follow that recommendation, because they know what material has been used, it's not only, whether it's iron or aluminium, it's also the type of rubber that was used on hoses and O-rings and that type of thing that can be influenced by the type of coolant that's in there. So it's generally safe to follow the OEM recommendation when you get questions, when they are strongly recommend a particular type or type of coolant be used. Is this coolant equivalent to other coolants on the market? Maybe, but we would need to establish that the chemistries are the same before you would be able to say, all right, we don't necessarily need to use product A as stipulated by the manufacturer. Product B may also work in there, but we would need to establish that the chemistries are very similar before we could make that recommendation. And I would suggest caution in doing that, and to, even in that situation, if they appear to be similar chemistry technology, I would still suggest maybe doing a trial with only one or two pieces of equipment initially to establish that the coolant does in fact work as well as the original coolant for that particular application.
We had another question. It says, how can reserve alkalinity be measured in milliliters? Is there a denominator missing or a percentage? I think this was around slide 24 or 25.
Yes, Kelly is correct. It should read milliliters per liter or milligrams per gram. Unfortunately, these slides came from a training slide deck, and this is something that hasn't been identified before. But yeah, we'll need to correct that on that slide.
No problem. Thank you. Also, where can glycol-based coolants be disposed? The city sewer?
No. The short answer is even the propylene-based coolants are advertised as being environmentally friendly and less toxic. I would still recommend that they be disposed of in a responsible manner. There are a number of organizations that do hazard waste removal, and they will generally have programs for common fluids like coolants. So I would suggest moving the fluid into that kind of waste stream. Some may even offer recycling facilities. So some people may be able to extract the glycol from the coolant and things like that, so that it could be reused in the future. And that's obviously even more beneficial than just letting it become a total waste product.
Is there any relation between pH and glycol percentage?
Yes and no. As we add glycol, we will tend to shift the pH value, and it's a small movement, and it's not really significant. So I'm not sure exactly what the person is trying to understand from that question. So maybe if they can explain a bit more. But essentially, we couldn't establish what the glycol content is purely by measuring the pH, if I put it that way. But we do know that as soon as we change the chemistry of water, we will change the pH. So one of the values that will move as we add glycol to water is pH. But you couldn't predict one from the other, if I can put it that way.
Okay. And there's another question that says, does those principles apply to refrigeration systems?
Short answer, no, but longer answer, it depends very much on the type of refrigeration systems. Refrigeration systems that use absorption type technology may have similarities. Refrigeration systems that are basically your liquid to gas type refrigeration systems, the whole nature of what is happening is quite different. In many of those systems, the refrigerant, actually, you've got to really keep water away from it. The refrigerant and water combination becomes very acidic. So I would say with refrigeration, it's a fairly different analysis that we need to do on refrigerants to try and understand what's going on with the refrigeration system. So I would say that there's limited overlap between what we do on coolants and refrigerants.
It looks like we have one last question. It says, if coolant is working properly, what life of coolant or what change period on a yearly basis?
This is a difficult question. In my experience, I've seen coolants typically lasting almost a typical rebuild life for an engine under ideal conditions. But I would say that this is in a handful of cases where I've seen this, where they were power generation. So it was a power generation environment where everything in the environment is very well controlled. The load on the engine was controlled. How the coolant was managed and topped up in these engines was well managed and maintained, and you generally have a fairly large coolant volume to engine output in this type of setup. And so there I have definitely seen that you can do this. As we move into mobile equipment, this becomes a lot harder to manage, and the risk of things going wrong are much higher. Generally, within mobile equipment, if you're using a hybrid style coolant, it would need to be a hybrid style coolant to have a chance of getting a long life out of the coolant. Generally, the coolant will need to have supplementary additive added at least once, probably in a service cycle. And then again, you could potentially get it to the life of your engine. So let's say you've got an engine that is scheduled to be rebuilt every 12,000 hours. I would say you could probably get the coolant safely to 8 to 10,000 hours, and then the extra 2,000 hours, the coolant's probably going to degrade, but you're scheduling the engine for a rebuild anyway. So is it that important that the coolant is degrading at that point in its life cycle? So it all becomes on what the priority is in terms of how we're managing the total maintenance cost of this piece of equipment.
Thank you, Gary.
I guess I should explain also a little bit. I see it's Jamal, I think, am I reading that correctly? His question is that
Yes.
the biggest problem that we notice with coolants is that they tend not to be maintained. And so people tend to ignore them. They will bring a machine in and they will do regular oil changes and filter changes and just ignore the cooling system. And I would suggest that people try and apply more attention to the coolant systems, by pulling a sample. If you take a sample from your coolant system, say 4 times a year, once every 3 months, you'll start to build up a much better understanding of what's happening to your coolant system, and then you can make a decision as to whether or not this coolant is safe to stay in there for prolonged periods, or whether you need to change it more frequently. And just a last comment on this, about 5 years ago, I had a phone call from a marine customer that I've been dealing with for several years. And this gentleman said to me, he started the conversation with, a couple of years ago, you were here doing training. And I said, yes. And he said, you told us to sample our coolants. And I said, yes. And he says, hell, I wish we had listened to you. We've just lost our main engine in our biggest vessel in peak season due to the coolant. And so I think this is the main thing that I'm trying to get across to people, is that coolants, if they're looked after properly, will work well for long periods of time and need little maintenance. But if they get ignored, the risk of doing serious damage to the equipment is high. So please don't ignore them.
Thank you, Gary. We don't have any additional questions at this time. I do want to let everybody know that this webinar presentation has been recorded. All participants of this webinar will receive a follow-up email once the recording is available to view. Also, we post our webinars on our ALS Global website and our ALS YouTube channel in the webinar playlist. And also feel free to follow our company page on LinkedIn. That's where we post announcements and registration links to future webinars and also other valuable resources and updates. Gary, thank you so much for presenting today and for everyone on this call. And hopefully everyone can enjoy the rest of their week.
Thank you, Kelly. Thank you, everybody, for taking time out of your day to listen to me.